Once again, you're traveling in a car when suddenly a policeman stops you. What will you do? There are two options. One, you can apply the brakes and stop the car, or the other way, you can accelerate and speed away. So what is acceleration? Acceleration is the rate of change of an object's velocity with respect to time. Let's walk through this. Imagine you have two vehicles, a truck and a car. Your truck takes 30 seconds to reach 60 kilometers per hour from zero, and your car takes just 10 seconds to reach 60 kilometers per hour from zero. From this, we can see how much the speed increases every second. Acceleration is final velocity minus initial velocity divided by time rate. The car's final velocity is 60 kilometers per hour. The initial velocity is 0 kilometers per hour, and the time taken is 10 seconds. So acceleration is 6 kilometers per hour per second. It means that the acceleration increases by 6 kilometers per hour every second. To more easily understand, we change the hours into seconds. Imagine the car is already in motion, with an initial velocity of 10 meters per second and a rate of acceleration of 5 meters per second squared. So at 0 seconds, the velocity is 10 meters per second. After 1 second, the velocity will be 15 meters per second. After 2 seconds, the velocity will be 20 meters per second. Thus, the acceleration tells us how fast the velocity is changing. Now let's delve into some real physics. During acceleration, we can feel a force pushing in the opposite direction. If the car accelerates forward, we get pushed backward into the seat. And if the car turns right, we get pushed towards the left. This basic example of classical physics is beautifully explained by the celebrated scientist Isaac Newton. Newton was thinking like this: if we throw a ball, why does it slow down and fall to the ground after some time? As we all know, he identified this as Earth's gravity pulling the ball down. Gravity is an external force acting on the ball, as well as friction and air resistance are external forces. First, we start with gravity. In this universe, everything has a certain mass. Two massive objects attract each other according to their mass. The more mass, the greater the attraction. Objects with greater mass attract lighter objects towards them. Therefore, as the Earth has more mass than the ball falls to the Earth's surface. The standard unit of mass is kilogram. But what is weight, and how is it different from mass? Mass refers to the amount of matter present in an object. It does not vary anywhere in the universe, but weight isn't like that. For example, if a ball weighs 10 kilograms on Earth, we will not get the same weight on the Moon. Why is that? As we already see, massed objects have a certain gravitational force. They pull other massed objects towards them. How powerful they pull depends on their mass. For example, our Earth pulls other objects at 9.8 meters per second square. This means objects accelerate at the value of 9.8 meters per second square towards the Earth's surface due to Earth's gravity. For comparison, the Moon's gravitational force is 1.62 meters per second square. So the weight equals the mass multiplied by the gravitational force. If the object's mass is 80 kilograms, we get their weight on Earth as 784 kilograms meter second squared, or simply 784 newtons. On the Moon, the same object's weight will be just 130 newtons, as we have multiplied 80 by the Moon's gravitational force, 1.62. Thus, weight is not the same as mass. It is a force. Thus, mass is the measurement of the amount of matter contained in an object, and weight is the measurement of how strong gravity pulls on the same object. Since weight is a force and gravitational pull is simply acceleration, we can rephrase it like this: force equals mass times acceleration. This is Newton's second law. F is equal to ma. This means that force can induce acceleration in an object. Acceleration depends on the amount of force applied, and heavier objects require more force for acceleration than lighter ones. For example, consider two boxes which have masses of 50 kilograms and 100 kilograms respectively. If you apply 20N on both boxes, the 50 kilogram box will have a higher acceleration than the 100 kilogram box. This means acceleration is inversely proportional to the mass of the object. If you want to accelerate a 5 kilogram box across a frictionless surface at an acceleration rate of 4 meters per second square, how much force do you need to apply to that box? Just simply put the values into this equation. You will get the answer 20N. Similarly, if you apply a constant 20 N force on a 5 kilogram box, you can determine how much the box can accelerate second by second. Here we use the term frictionless surface. What is that? We already see that friction is also an external force. When the surfaces of two objects contact each other, a force is created that acts on each object. This force resists the motion of the object. Some surfaces have more or less frictional force than others. For example, the surface of glass has less frictional force than rough surfaces. For example, when we apply the brakes to a car, the car's tires stop rotating and press firmly against the road, creating increased friction, which then causes the car to stop much quicker. The same reason behind this is present when we drive during rainy days, because water has low friction. The road and the car's tires are unable to press so firmly together, and so we feel the effects of slipperiness while driving. Then, what if there is no external force acting on an object? This is where Newton's first law of motion comes into play. Every object will remain at rest or in uniform motion in a straight line unless an external force acts upon it. Uniform motion refers to constant velocity or no changes in the velocity. For example, imagine you're traveling in a car at constant velocity. You won't feel any force on your body. You feel you're stationary, but once you accelerate the car, you can feel that some force pushes you to the seat. Similarly, when applying the brakes, the friction force resists your velocity. When the car's movement suddenly stops, you're pushed forward. Another example is the electric fan continuing to spin for a period after the electricity is turned off. What brings the spinning to a stop are external forces such as air resistance and motor's friction. These are examples on Earth. But we know that the Voyager spacecraft is traveling through space without using fuel or engines. This is also because of Newton's first law of motion. In deep space, there are no external forces such as friction, gravitational pull, or air resistance. There is no force bringing the Voyager probe to a halt, so it remains in constant motion. Unless an asteroid or space rock of some kind collides with Voyager, there is nothing that can change its velocity. Now imagine a ball placed on the ground. It is at rest, but how does it remain at rest? Because gravitational pull continues to be applied to the ball. It pulls the ball towards the center of gravity, that is, the center of the Earth. Simultaneously, the ground applies an equal force in the opposite direction. This is called the normal force. These two forces balance each other, so the ball remains at rest. Now the object's net force is zero. If we want to move the ball, we need to increase the net force. So now a boy kicks the ball and it gains some net force. Therefore, the ball is in motion. But eventually, after a certain time interval, it stops moving. Why? Because there are other forces such as friction and air resistance applying from the opposite direction. The ball stops. However, when you kick a ball, you can feel a noticeable sensation of feedback in your foot. This is because you are exerting force on the ball, and at the same time, the ball is also returning some force to you. Here comes Newton's third law. Every action has an equal and opposite reaction. For example, when you jump, your legs apply a force to the ground, and the ground applies the equal and opposite reaction force that propels you into the air. The best example of the third law is rocket launching. When a rocket launches, the rocket engine produces hot exhaust gases that float downwards at extreme speed. Because of the opposite reaction, the rocket gets pushed upwards. This force is greater than the rocket's mass, and it's also greater than the Earth's gravitational pull, so the rocket lifts upwards. Once a rocket successfully launches from the launch pad, the second law of motion applies. F is equal to ma. The rocket receives the same constant force from the fuel expulsion, so it gets momentum and gains acceleration second by second, and the rocket's speed increases. Once it escapes the Earth's gravitational pull and enters space, there is no external force to stop the rocket, so they turn off the engine as it already has momentum. Newton's first law applies. Without fuel, the space